Okay, let's get started. Oh, Nick and Alfred, they all went somewhere on vacation or something. Go fishing. Okay, welcome to HAO Colloquium today. It's indeed my great pleasure to introduce our speaker today, Rit Carbone. Rit is now emeritus senior scientist at NCAR. And Rit is a pioneer in Doppler radar for atmosphere studies. He has conducted research in physical processes in clouds and storms, topographically influenced circulation. You're in the right place. Predictability of warm season rainfall, severe storms, and convection on tropical islands. And that explains his stay in Hawaii part of the year to investigate that aspect of his
Very
research.
important. I'm quite conscientious about that.
That's right. On the service side, Rit led the United States Weather Research Program until 1999. And also he chaired the World Meteorological Organization, WMO's World Weather Research Program from 94 to 2001, and served as the vice president for the International Union of Geodesy and Geophysics. He's a fellow of the American Meteorological Society. And 2001, Rit received a Cleveland Abbey Award for distinguished service to atmosphere science. He has also received 3 outstanding publication awards from NCAR, and today's work will be his awarded work last year. And here's Rit.
Thanks, Hanli. I want to make one small correction to your introduction, and that is the 1982 publication prize was a very odd situation, and BC Low is the real winner. The committee couldn't make up its mind who should win. The NCAR director at the time said there was no way he was paying for 2 of them. BC got a medal and a check. I got a medal. So BC is the true winner. So anyway, still, it was an honor of sorts. But you know, Bill Hess was in HAO's corner in those days. You remember those good old days with Bill. So anyway, it is a pleasure to have the opportunity to speak to you today. I've interacted over the years with a number of people in HAO, including several of you present. BC and I were and are good buddies ever since the 1982 introduction to each other. And so I'm sorry he can't be here today. I am going to talk sort of mostly about the paper that won last year's award, but there's more recent work that I'll spend a little bit of the time on. This is a unique experience for me in the sense that while I've spoken to many diverse audiences all over the year, never have I spoken to an audience whose expertise did not significantly overlap with my own, and vice versa. So I was a bit in a quandary about what to do with this. I'll try to stay away from meteorological jargon, and if I do that inadvertently, please alert me to that difficulty. So today we're talking about a rather old issue in tropical oceanic rainfall, and to sort of put it in perspective, all current global models, especially global climate models, are highly parameterized and assume that a high SST is the fundamental cause of rainfall over tropical oceans. This study results give partial credit to that view, but with, I think, a major new insight. World-class scientists have studied this problem over the past 20 years or so, and you see Ramanathan and Collins and Needland and Held, world-class scientists, examined this problem and came up with the conclusion that indeed it is the absolute value of SST. Ramanathan referred to it as the thermostat hypothesis. Okay, and then there was Dick Lindzen from Harvard and Sumant Nigam, who took the contrarian view that the SST gradient's more important than the actual SST in determining the vertical air motion in the lower troposphere. There are good reasons for this confusing among brilliant investigators is that it turns out that SST and properties associated with the gradients thereof are covariant to a considerable degree. So it's very difficult to separate correlation from cause. And this work attempts to do that with some rather significant statistical results. So the two studies, the one that won the last publication prize is in that box labeled Tropical Western Pacific, and over a 49-month time series of observations from space, it examines every single rain event, which is greater than 10,000 events over that 49-month period, its precise place and time of its origin, and its evolution. It also examines the SST structure, including the gradients themselves and the Laplacian of SST, i.e. the curvature of the gradients. And that latter quantity turns out to be crucial to the discrimination between the role of SST and the Laplacian of SST. The observations used are all from low Earth orbiting satellites, basically all of them, whether they're in polar orbit or otherwise. This product, the Global High Resolution SST, has a number of centers around the world, principally located in Europe, but also facilitated at JPL in the US. It's pretty high resolution, spatially, temporally. It's daily data. So for example, no consideration of diurnal variation can be taken into account. They are simply daily averages. In our case, we chose, in the spirit of the mesoscale matters, to examine only the mesoscale forcing functions, where mesoscale is typically on scales from a few tens of kilometers to maybe up to 150 or 200 kilometers in this particular study. All previous studies have only examined the large-scale forcing, because in the tradition in meteorology is that the large scale rules. And it does rule in the sense that large-scale forcings do a lot of hard work associated with the deep troposphere. However, the excitation of deep moist convection is fundamentally limited by, and that's the deep troposphere is the free troposphere, by the planetary boundary layer. There will be no moist convection of any depth if there isn't success within the planetary boundary layer. And this is kind of the fundamental limitation of previous studies and their conclusions. So we took upon the onerous task, and I should say that my partner in this crime, Yanping Li, did a lot of very hard work as a postdoc to apply the analysis of high-order polynomials to obtain the first and second derivatives of the SST fields, and trace back in time to the beginning of all precipitation to see what was the surface condition of the ocean for each of those 10,000 plus rain events. The rain itself is identified from an NCEP, our National Weather Service product called CMORPH, which is a combination of microwave and IR data. And it uses the microwave to determine rain, no rain, and the quantity of rain. And it uses the IR information to interpolate over time, which the IR data is good for from cold cloud tops. It's a very sophisticated product in both cases. The quantity of rainfall is considerably uncertain under certain circumstances in CMORPH, but the SST data is basically as good as you could imagine observations from satellite with 25-kilometer footprints can be. So anyway, we define the onset of rainfall as a minimum of 5 pixels in that CMORPH data set with a central maximum of equaling or greater than 1 millimeter per hour. And then that defines the condition of the SST structure underneath.
So can you give us an idea to what accuracy this data would determine rainfall? Like in May we had in Boulder 6 inches of rain. To what accuracy would the satellite observation be able?
There are considerable inaccuracies. The important thing here is that we don't use the rain. We use the rainfall as yes or no. Okay. Primarily, there are some things I'm not even talking about today where we invoke the quantitative amount of rainfall. But basically, there's this general category of cumulative rainfall that will be highly correlated, especially with SST, as you will see, but have little or nothing to do about the onset. Whether there's rain or no rain, even very light rain, the CMORPH data set is very accurate. Okay?
When they measure the sea surface temperature, I don't know if you're going to talk more about the microwave measurements, but can they see through the rain? Do you understand what I'm asking?
Through light rain, yes. When the rain is beyond a threshold that I can't remember, it is that rainfall, that grid point is disqualified from consideration. It's masked out, and then it is subsequently interpolated based on the conditions that were observed before and after the rain. Yeah, yeah, yeah.
Presumably the sea surface temperature doesn't change temporally that rapidly.
It does when it rains. We'll talk about that in a minute. It doesn't change much. It's a small amount, as you'll see, but in fact it changes rapidly right at the time of a convective event. So anyway, so all this sea surface temperature stuff has nothing to do with topography here, but I'm using these examples here because in all of these instances, everything is a close cousin in the sense that whether deep moist convection is most common as resulting from sea breezes or from elevated heat sources such as major cordillera over continents. And that is a close cousin to, say, warm patches of water in tropical oceans, which are neither elevated nor do they involve any terrain, okay? But they have a similar effect. And so the investigation here is whether that subtle effect of warm patches in ocean have any impact on the actual excitation of deep moist convection. So these are, and what they have in common is that they result from thermally direct solenoidal circulations, where the heat source is at the upward branch of the solenoidal circulation, and there's a descending branch somewhere, the scale of which is dependent on a lot of factors we won't discuss here. So here I'm showing you mountain plain circulation on the left and mountain valley circulations at a smaller scale, and then your sort of typical tropical island, which is flat and wet, and to the atmosphere looks pretty much the same as the water itself, but slightly different. The fluxes of certain fluxes are higher over these tropical island land masses. And I know this from experience in previous studies at the Tiwi Islands north of the continent of Australia, where in fact these breezes create what is argued to be the strongest thunderstorm in the entire world. And navigators of aircraft relied on seeing it a few hundred kilometers away in order to, a long time ago, to see that they were flying in the right direction towards some part of Australia. So we're referring to the current problem as blue water breezes, and these are transient warm patches of ocean. They'll only last a few days, maybe a week, maybe in the extreme, 10 days. They're gone, and some other part of the ocean has similar warm patches. Okay, and this is why they're very difficult to track down. They're not at a fixed geographical location. So the process involved here is to emphasize the Laplacian of SST. And so on the diagram there on the right, you see a hypothetical SST gradient of magnitude 1 degree, which we knew a priori was a typical magnitude for gradients in the tropical Western Pacific. And so in the second panel, of course, is the hydrostatic pressure response to the higher SST, and therefore the warmer and less dense marine atmospheric boundary layer. The third panel is the Laplacian of SST, or del squared of SST, and you can see that where the curvature of the gradients create at the baseline of the curvature, meaning, let's see, what do I do to make this work? Oh, there it is. Okay. So the concave curvature is the divergent side of the Laplacian of SST, so it's positive Laplacian. And the negative Laplacian is the convex curvature. And it's the convex curvature that actually causes the convergence, where you see the fastest wind speed, this perturbation between the arrows left and right, creates convergence between it and the, let's call it the downstream location, and divergence here on the upstream at the base of the SST gradient. It's a simple hydrostatic pressure response. The rotation of the Earth has no impact on this circulation because we're at the equator, or so close to it, it doesn't make any difference at these small scales. So anyway, the magnitude of the Hadley-Walker circulations, which are large-scale circulations that are conditioning the deep troposphere and doing so very, very well, but don't do much in the boundary layer, is really swamped by the magnitude of this small-scale divergence by a factor of 10 to 20. So we find that the boundary layer convergence, based on a simple, idealized 1 degree temperature gradient and its curvature, is basically 3 to 7 times 10 to the minus fifth per second, whereas Hadley-Walker, if I can go to the next one, I guess I should have shown this, but that's where the convergence is occurring. Oh, and the point here is that that convergence is going to be at an SST that's about 0.25 degrees warmer than the average SST in this gradient, because it's about halfway up on the curve above the mean. And we'll see if these hints on how it should behave actually result from the computations. I'm not going to go through all of this, okay, except the breeze is kind of the pull of the warm spot. The gravity current approximation is the encroachment or rush of shallow cold air toward the warm spot, based again on density of the fluid and pressure differences. And so we see again that in the lower left, the background convergence, which is the maximum you get out of the Hadley-Walker circulations, is an order of magnitude or more lower. So it looks like we have a chance to see an effect from all of this. Okay. So let me start from the bottom with the SST panel. This is the SST climatology for this patch of ocean in the tropical West Pacific. And you can see that the range of temperature isn't very large. It's really only occupying the central portion of the color scale there. It's probably less than a degree, maybe 0.7 of a degree or something like that. Gradients are extremely weak. This is the kind of data that previous studies used to determine whether the gradients were important or not, because there is no such thing as daily high resolution SST from satellites. Some other studies used monthly averages, which aren't much different from this. So this is one day in July of 2009. And so let me show you what the daily SST looks like. A little different, huh? Lots of gradients. Some in excess of a degree. And the little diamonds in there, black diamonds there, are the 7 locations in which a rainfall event was excited on this particular day. Statistically, this is very average for the entire data set. On average, there are 7 events per day. There are 7 events on this day. And the range of SST variation, not the specific locations, but just the range of variations, is also very typical, especially for the boreal summer period. The gradients associated with this field. Oh, Michael, you have something to say?
Yeah, what is the accuracy of the satellite measurement of the sea surface temperature?
It's better than 1/10 of a degree.
Okay.
Okay, probably about 700ths or so. We looked into that originally. My memory is a little fuzzy, but it was good enough for what we're doing with it. Anyway, you see the gradients, and they have a kind of a cellular and serpentine look to them. They sort of change gradually over a period of a few days, their location and amplitude. But there are plenty of them, and some of them are quite large. Some of these event excitations are really not particularly sensitive to the amplitude of the gradient. So it turns out there's a sort of less covariance between the amplitude of the gradient and the amplitude of the Laplacian than one might expect. The Laplacian field is up at the top. It's just a bunch of dipoles where red is convergent and blue is the extreme of divergent. Averaged over all time, the Laplacian field is 50-50, half and half, averaged over all time, but on any given day it can deviate quite substantially from that. So there are, I don't know, 300 or 400 Laplacian dipoles here, but only 7 rain events. So it gives you an idea of what, it's about 2 or 3% at most that activate on a particular day. So this is some correlations with rain in that same domain, but for the entire 49-month period, all rain is at 0 at the black line across the middle, okay? Okay, all rain is collapsed to that. Preceding that, above that is the 10 days prior to the occurrence of rainfall, and to the bottom 10 days after. You see that the SST, the Laplacian of SST, and the amplitude of the gradients are all in quadrature. Both SST and the Laplacian of SST lead the rain. In the case of SST, it's 1 to 2 days. In the case of the Laplacian, it's 2 to 3 days. But the gradients of SST actually increase as a consequence of rain and consequently achieve their high magnitudes, lagging SST by, on average, 2 to 6 days. So it's actually the rainfall events that create the gradients, and the gradients are basically sort of either average or at some minimum prior to the rainfall event itself. That's not an event, and that was not our expectation when we went through these calculations, by the way. So anyway, they're all in quadrature. So was the first result that kind of knocked us off our seats, because we really didn't know if any of this would work and whether the signal, we were hoping even for the weakest signal to show some significance to this work. So the black curve is the background distribution, all 49 months, okay, of the SST distribution. You see a very cold tail on that. That's boreal winter in the northern 5 degrees of our domain of computation, where sea surface temperatures up around Guam get quite a bit cooler than things closer to the equator. The red line are the SST's frequency at the onset of all rain events, so all 10,000 events. So a lot of those dots are histograms. Basically all of them are histograms, since you wouldn't want to look at 10,000 dots, I don't think. And anyway, you see that the highest area normalized frequency and absolute frequency is at the mode of the SST distribution. It doesn't favor the highest SSTs, and it disfavors the lowest SST, which is winter encroaching on the domain. The mean of the two distributions are separated by, guess what? 0.23 degrees. We expected about 1/4 of a degree. So and I'm on the wrong diagram for that. Let's go to the next one anyway, where we have the Laplacian, and so we look at the background Laplacian distribution is the black curve. It is not absolutely 0 frequency at 0 as it shows there. It's very close to it. It's a very deep minimum, but we couldn't calculate the actual very, very small values with statistical significance, so we labeled them 0. So
can you explain what background means again?
the background,
Yeah.
what about it?
What is it again?
The whole area of computation for all 49 months.
At what time? Just
Well, they're daily data, so all days are averaged. Okay, and it's not perfectly symmetric, but it's very, very close. The red curve is the condition of the surface ocean the day before onset of rain. 75% are over the convergent Laplacian of SST. 25%, actually a little bit less than 25%, are on the divergent side. This was a gigantic signal that we, again, did not anticipate, but the fact is that it holds up to all kinds of subsequent tests of data and results as being completely consistent with how nature seems to work in this case. And that is that the mesoscale forcing is intrinsically so much stronger and effective at creating vertical velocity, vertical kinetic energy, strong enough to break through those layers of static stability at the top of the marine atmospheric boundary layer. It's a very common feature at the top of boundary layers throughout the Earth where there's a layer of static stability. And there's separate circulations from the large-scale circulations that which deal principally with the free troposphere. The boundary layer has its own dynamics, its own turbulence, its own ability to adjust itself according to the lower boundary fluxes and other considerations. So this was a surprise. By the way, this is what the surface ocean looks like in blue here the day after rain ceases. And it's suddenly the Laplacian structure of the SST is net divergent, 60-40 divergent. If you look at the bivariate distribution of these quantities with SST on the vertical axis and Laplacian on the horizontal, and this is before onset and after onset, left and right, you can see the shift of these values, and there are subtle changes in temperature in here where the after is about 0.15 degrees cooler than the before. So, why show us some proof that this is really happening? And so we looked at, again, the background of the entire time series, which is the lower curve that's been averaged over whole months. So keep in mind we have about, I don't know, 100 times more data in that bottom curve than the upper curve. The bottom curve is the background distribution of Laplacian forcing. The upper curve are only those locations where rainfall events occurred. And that's about, I don't know, 2 or 3% of the total background number of data points. And you can see they have a very similar shape. The dash curve at the fine curve at the very bottom is just the upper curve transposed to the background values. And the difference between the two is sort of square root of 3 ratio, which means that the vertical velocity created in the atmospheric boundary layer is the vertical kinetic energy, I should say, is 3 times that of the background. So it turns out to be a rather strong forcing. We're talking about vertical velocities that are 3 to 8 meters per second at the top, not meters, centimeters per second, top of the boundary layer, whereas the background forcing for Hadley-Walker circulations is about 3 millimeters per second. So it's a very big difference, and it's also a very big difference between those locations between where rain events actually occur as opposed to the whole ocean, which is relatively weak in comparison. And again, you see that the sort of northern hemisphere warm months, those months tend to be to the right of the minimum, and the cooler months to the left. Notice that it requires less vertical kinetic energy at the temperature, which is about 29.45 of the mode of the distribution, of the SST distribution. So it turns out there's less convective inhibition, which we call SIN in meteorology, C-I-N. The minimum resistance to deep moist convection is right at the mode of the SST distribution. There is no preference for high SST, and there is, but cool SSTs in that northern hemisphere winter are disfavored. So there's a kind of a cycle that goes on here, and this is kind of in connection with the Madden-Julian oscillation. This is very qualitative, but you get this covariant buildup of both SST and the Laplacian of SST in a period just before the atmosphere is sufficiently conditioned to excite rain events. The rain events cool off the ocean a bit and create very large magnitude gradients, so temperature gradients on the surface ocean. The atmosphere gradually recovers from all of that and begins to restore itself and return to the initial state. And that is anywhere between an 8 and a 14-day period for that recovery to occur.
Great.
Yes?
So if you have, at the recovery phase, you have a strong divergent flow, right? If you have more divergence branch.
That's right.
Will
It's
that,
net divergent.
will that create some strong convergence in neighboring kind of areas?
Remember, this is all very small scale. So, you know, we're dealing with scales of this that are a few tens of kilometers at the most. So in terms of when you say large scale in meteorology, large scale is 1,000 to thousands of kilometers, even 10,000 kilometers. You know, low wave numbers on a planetary scale. So yeah, locally, you're going to get, you can't have a completely divergent ocean surface, right? So it's net divergent is all I can say, and I don't have any figures in here to show that, but a larger area fraction of the ocean is divergent. There's convergent and divergent regions, but it's say 60-40 divergent, and the recovery is to bring it back to slightly net convergent over that period of time. All right, this is just a cartoon kind of illustrating this sort of thing before the rain and after. But perhaps I can, there are a lot of factors that can affect this asymmetry, the majority of which are probably in the upper ocean and not in the atmosphere or on the very surface of the ocean. And this makes attribution, shall we say, to of the process very difficult. It even goes into chlorophyll in biology, which can cause the greater part of 1 degree variation in sea surface temperature at higher concentrations of chlorophyll. So there's static upper ocean stability and dynamic upper ocean stability currents and that sort of thing, which get very complicated. So to put a little more meat on these bones here, these are what we refer to as Hofmüller diagrams. I don't know if those exist in your world, but okay, each column there is a year at a different latitude. So on the left we have the equator, then we have 7.5 degrees north and 12.5 degrees north. And you see they have different characteristics. But one characteristic is common is there's a lot of time variation. And in the case of at the equator, there's a zonal gradient as well, where in the western part of the domain, by the way, the reason some of these data are missing over here is because the island of New Guinea was very uncooperative and wouldn't allow us to do our derivatives. Because we have to use these long polynomials in order to get the results out. So we couldn't get results on the very western edge at the equator because of the island of New Guinea. But anyway, that's kind of aside. You see bluishness, which is Laplacian divergent, and redishness, which is Laplacian convergent. So at the equator, we see net convergence on the west, then periodic net divergence toward the east. If you look at 7.5 degrees north, which is approximately the ITCZ, intertropical convergence zone in the northern hemisphere, we see more distinct periodicity here between redishness and bluishness, convergence and divergence. Some hint of a little bit of maybe propagation of some of these bluish areas anyway, but overall relatively balanced. The white spot is a failure of a satellite at that latitude. Not one satellite, but the satellite product, shall we say. And then at 12.5 degrees north, which is kind of Hawaii-like, you might say, it's somewhat seasonal. And so the cooler half of the year, the cool half of the year is the top and the bottom. Ocean summer is over here. They all have these extrema in the climate, have high amplitude Laplacian forcing of both signs, but the transitional seasons, very low amplitude Laplacian forcing.
So you're saying with 3/4 of the events, the rain events are convergent. What determines when something is convergent? That doesn't mean it's going to be a rain event, right? Is that
No, but remember, the 3/4 is based on where and when rain started.
Right.
And it's Laplacian-induced convergence. By definition of where it occurred, the curvature there was Laplacian convergent.
Okay, so 3/4 of the conditions that are set up are going to have rain events. Is that would be? Just want to make sure I understand.
3/4.
In other words, if those conditions are there, in other words, you had areas that were convergent here on these maps. So what is the probability of these rain events when I look at your maps here? Looking at the SST, the
Well,
gradient, and here's the Laplacian.
this is time and longitude, and not, these events are not identified here. This is just the Laplacian field and its variability.
I just looked at that though, and I overlap where the rain events occurred.
Oh, you're going to see where the rain events occurred on the next slide. Let's get to that, okay? Where's my arrow here? Okay, so I just took 2 of the latitudes. I think it's what, the equator and 12.5, the 2 extremes. And you can see the amount of rain is in those sort of brownish, reddish, yellowish streaks. Those are all rain events. And what you'll see is where it tends toward blue, there's very little rain, typically. Where it tends toward red, typically there's more rain. This is not one-to-one, mind you. There's a correlation here, but it is variable. And I just, without attempting to become more quantitative, is just to show the sense of variability. So this seasonal stuff, you can see here's a lot of rain, and it's sort of mixed forcing, but sort of preferentially red to some degree. You find other places where they are not in agreement for reasons that I think would be difficult to quantify. But this is kind of like this big blue patch here. That's kind of like the red spot on Jupiter or Saturn, wherever it is. It's so big and so strong that the chance of any rain is really greatly suppressed during that time. I mean, you have to look at the time period here across here. It's just almost pure white. Almost no rain. So this is not to say that the Laplacian forcing is the dominant cause for the sequence of events at all times and all places. It's not. There are many other factors that come into play. But the point is that there's a generally physically plausible correspondence between the variation of the 2. So, yes?
So from the streaks, it seems that means the onset of rain is occurring almost at the same time over a very wide range of
Well, no, there's a slope there. Remember, those are whole years. So a small slope is, about a week. So yes, there is propagation. In fact, that's kind of a different subject that I chose not to talk about today. Where there's propagation, there is sufficient vertical shear of the horizontal wind. And when that vertical shear of the horizontal wind reaches 10 to the minus 3, then convection organizes from ordinary convection to mesoscale convective systems that are long-lived and propagate. And there's a whole set of slides on that stuff that's not part of this talk today. But
what altitude is that shear? That's very short shear.
well, between the upper troposphere and the lower troposphere, say 10, 12 kilometers. And so basically you need a meter per second per kilometer, as I recall. So once you get to 10 meters per second vertical shear, you know the convection will be organized. This is true anywhere over continents, oceans, doesn't matter. It's a universal rule of organized convection that isn't completely understood. But I'll give you the simple answer is when there's vertical shear of the horizontal wind, the updrafts and downdrafts inside the convective storms are not vertical. They're tilted. They're actually tilted into the wind with height, increasing height. And that means upon the formation of precipitation, when it sediments out, it's not falling back into the updraft, which it does in ordinary convection, which kills the storm. That's why thunderstorms are very short-lived. But in the presence of shear, the sedimentation of rain and the diabatic cooling that goes with it falls outside the updraft. And so it's actually a very efficient heat engine in the condensation of all that water. And when it sediments out, it's not cooling off the source air that is the continued source of the updraft. We're a little off topic here, but anyway, I hope that's helpful. So anyway, you sort of get the general drift of this stuff. I thought I had eliminated this slide. The European Center for Medium Range Prediction did an interesting experiment, knowing nothing of my research, fortunately, and they did this hindcast. They took a set of initial conditions and then ran their model forward, their research model forward, in a number of ways, and treating sea surface temperature as persistent, fixed values, monthly averages, a couple of coupled models, and then daily SST data and weekly SST data. And they fully expected daily to win the race. To continue above this dash line means there's skill in prediction of the Madden-Julian oscillation, which is the most important free tropical wave on the planet that causes most of the rain in the tropics. But what happened is the result turned out to be weekly, not daily. Why is that? Why would the weekly SST data averaged over a whole week's time be more skillful in maintaining the Madden-Julian oscillation in the forecast model? Well, the answer is, I think the answer is, but it's not guaranteed to be the right answer, that's for sure, is that these are the Laplacian anomalies, just 1 month's worth here to show you an example of how long they last. And it turns out that they have a large amplitude, typically between, say, 6 and 10 days duration. So if you do daily SST, not a whole lot changes from one day to the next. Whereas if you do weekly SST, you get a much better average of the strength of the forcing because you've reduced the errors in the SST measurements themselves by reason of slightly larger numbers, okay? So it turns out that weekly provides a better forecast because you get to work over the daily data, say 7 times, and reduce the errors in the fields through that means where the mean condition actually hasn't changed significantly. Didn't mean to talk about that. This is MJO Band-pass, 30 to 60 day bandpass filters placed on the data. Again, this is probably a whole year for a whole world. And anyway, the sort of red areas on the left-hand side of the eastern hemisphere where lots of rain is falling, and that's the active phase of the MJO. And in between, you have the suppressed phases, both before and after, where less rain is falling. If you look at the anomaly correlations here, this one is the phase of the MJO, which is defined by sectors around the planet. Here we're only dealing with the Indian Ocean and out to the dateline. And with the maritime continent kind of in the middle here, which is sort of half mountainous land and half water. And the anomaly of precipitation are these contours around here. And here it is. And what's the difference with that bottom one? It's forgive me for my lack of memory of the difference between these two figures, but basically the anomaly correlation. So these are the raw data, and that's what that is, the raw rainfall data, and this is the anomaly. It's all anomaly here, so it's been simply established the whether it's anomalous positively or negatively based on the overall forcing. So, so this is the progression, the normal progression of the MJO eastward. It turns out that both the SST and the Laplacian of SST lead the phase of the MJO by almost one full phase of the MJO. This is too complicated. I don't want to go into this. But this is the most important slide of the whole talk when it comes to the relationship to the MJO and the implications for the importance of SST versus the Laplacian of SST. This is the Laplacian of SST across the eastern hemisphere again, out to the date line here. This is Africa over here. Okay, it's my version of Africa. The rest of it is mostly water, except for the maritime continent. And these are the different phases of the MJOs. This is phase 1, phase 4, phase 7, as defined by objective means by the folks in Australia related to the winds and other things. But it's an accepted index for where the MJO is and how strong it is. And you see that in the case of the Laplacian of SST, the high correlation with the rainfall actually leads the MJO itself by about 10 days and overlaps with the active phase of the MJO. Okay? So across the eastern hemisphere. Now what do you think it looks like for SST? Anyone want to hazard a guess? No one ever does. Oh well. This is SST. Same data set. Only we're dealing with SST instead of the Laplacian forcing. And you see it's always there. It's always highly correlated. It doesn't move. It doesn't even move when there's no rain there. But if it rains more if the SST is elevated, as it is in these cases. I don't know. This has, shall we say, been considered essentially as proof, even though it's not proof in the strictest sense of the word, that Laplacian forcing is more important in the frequency of rainfall events than SST. And SST is more important to the cumulative rainfall. In other words, given that there is an event, it will rain, it is highly likely to rain more when the SST is warmer. And that's the basis for the correlation of SST with rainfall. It's an if statement. It's conditional relationship to rainfall, not a cause for the events occurring in the first place. These are wave dispersion diagrams from left to right. They're the sort of power of rain on the left, of the Laplacian forcing in the middle, and the SST on the right. and this is done specifically to examine the relationship to the Madden-Julian oscillation, which is an eastward. The right-hand half of each diagram is eastward propagation. The left is westward propagation. The MJO, without fail, propagates eastward. It has wave numbers from wave number 1 to about wave number 7. And it has a period of, in this diagram, from about 20 to 80 days, because the filter is broader than the oscillation itself, which is 30 to 60 days. And to make a long story short, the best reproduction of where and when the rain occurs in the MJO is with the Laplacian of SST, which is in the 30 to 70 day period with about a 45 to 50 day average, and has the exact span of planetary wave numbers from about 1 to 7 or 8. The SST is basically kind of a dispersion field, kind of in both directions. The time period in which it builds up a little power down here, mind you, the MJO has no real power at a lower frequency than 70 days or so, and where it's beginning to build up its power is close to 120 days. And so it's kind of occupies some of the space of the MJO itself, but it's also symmetric around 0, so there's just as much on the opposite direction as there is in the eastward propagation. So the SST doesn't really jive with the MJO very well at all. So, conclusions. Hanli, you want to say something?
I was wondering about the dispersion relation, whether it's because the LSST, the Lagrangian Laplacian, kind of took out some of the large scales, because you would think if there's an anomaly inside the Laplacian, you should also have an anomaly in the SST itself. Let's say if you have some kind of wave structure, and if you see that in the Laplacian, I mean, that should also exist in the SST anomaly itself.
I'm not sure I get your point.
Say there's think of it as a wave.
Oh.
In the that there's a wave, you see that wave's signature in your Laplacian.
Yeah.
Would you also expect to see that in the SST itself, because the Laplacian is just the differential of that, SST.
Right.
So, I mean, then that wave signature, you would think it should show up in both the derivatives and the quantity itself. So I don't know why you do not see that in your SST.
I'm not sure I can, off the cuff, give you a decent answer to that. It can have wave energy, but it doesn't necessarily. It's not necessarily coincident with the period that defines the MJO. It can be at the edges or off the edges. It can be propagating in the opposite direction, which wouldn't be the MJO. There's evidence of both of these. There's some overlap because there is a lot of rain, although this is not about rain. This is just the SST. It has nothing to do with rain. All you can do is really look at what the rain does, which is sort of proof of what the MJO is doing routinely. And these are all the MJOs over the 49-month period, by the way. And the fact that there's a similar power, not exactly the same, but very close, actually, the maxima being almost identical in the case of the Laplacian. The MJO has a lot of, power in a lot of places and frequencies that don't relate to the MJO. I'm not saying they're not important. They could be important in a number of ways, but they're not the MJO. And yet the MJO is the most important free wave in the tropics, or for that matter anywhere, when it comes to the production of precipitation on planet Earth. There's nothing more important. And that's from Raoul Madden, from what we now call CGD, and Paul Julian, what we now call EOL. Okay? So these guys, Madden and Julian, probably have published the most famous papers in all of meteorology. Most highly recognized, for sure. So I think that's it. Oh, well, so I've already said these things. The inferred role of the Laplacian forcing is production of vertical kinetic energy. This is directly related to the onset and increased frequency, or decrease if it's weak, of rainfall events. The inferred role of SST is in production of moist static energy, and it definitely does that in spades. You warm up the SST, there'll be a hell of a lot more water that can condense in the troposphere if somehow it manages to ascend and start the process of condensation. That's something that SST itself doesn't do. There's no statistical evidence of it, and there's no reason for it. It's static energy, and not one drop of rain has ever been produced from moist static energy. The confusion here is that these are substantially covariant, and therefore it obfuscates their respective roles. And I consider this to be the principal reason why there's been so much confusion in our literature over the past 20 or 30 years. And I think all this suggests that since all highly parameterized global models presume that elevated SST is the cause of rainfall in the tropics. It's just the way the parameterizations are formulated. And that means that given the variability you've seen here with respect to SST and LSST, there should be rather large rainfall errors in these global models, and in fact there are. The worst place in the Pacific, believe it or not, has a rainfall error. This is in the CESM of 4 meters per year. The error in rainfall is 4 meters per year. That isn't even, there's less average rainfall than that. So, and this whole study has been motivated by sort of attempting to discover at least one of the reasons why the errors in the global climate models occur, the real cause for them, so that first of all we can gradually become more explicit in our representations in these models, and secondly that even when not explicit, we can formulate parameterizations that deal with the real cause of forcing these events. So, thank you. And I'm sorry I took so long.